Section 6.4, the central limit theorem. The central limit theorem for all samples of the same size n with n greater than 30, the sampling distribution of x bar can be approximated by a normal distribution with mean mu and standard deviation sigma over root n. Central limit theorem and the sampling distribution x bar given. First, population with any distribution has a mean and a standard deviation. Simple random sample all of size n are selected from the population. The requirement for using central limit theorem: population has a normal distribution or n is greater than 30. So the requirement must be one of these two. Your population either be a normal distribution. If not, then your n has to be greater than 30. To find the mu of x bar is actually just equal to your original mu. Sigma of x bar is equal to sigma over square root of n. And here is the conversion. If the original population is not normally distributed and n is not greater than 30, then the distribution of x bar cannot be approximated well by a normal distribution, and the method of this section do not apply. So always make sure that your original population is a normal distribution or your n must be greater than 30. Example 1. The elevator in car rental building at San Francisco International Airport has a place card stating that the maximum capacity is 4,000 pounds, 27 passengers. This converts to a mean passenger weight of 148 pounds when the elevator is full. We will assume that the worst case scenario in which the elevator is filled with 27 adult males. Assume that adult males have weight that are normally distributed with mean of 189 pounds and standard deviation of 39 pounds. A. Find the probability that one randomly selected adult male has a weight greater than 148 pounds. In this case, I just want to find the probability of one randomly selected adult, which means I don't even need to use a central limit theorem here. I'll just use a regular normal distribution to find the probability. Everything on the horizontal scale in this case representing the weights of male, which is x. My mean is 189. And I want to find the probability that the weight is greater than 148 pounds. Stat, calculators, normal. My mean is 189. Standard deviation is 39. I want x to be greater than 148. This is my answer right here. And I got 0.85343547. I'm going to round it to 3 significant figures. So I got 0.853. Question B. Find the probability that a sample of 27 randomly selected adult males has a mean weight greater than 148 pounds. And I am still using the same information for question 1. The weights are normally distributed with mean of 189 pounds and standard deviation of 39 pounds. So my mean is 189. My standard deviation is 39. I want to find the probability of a mean weight of 27 randomly adults. So right here, instead of looking for the probability of one adult, now I'm looking for the probability of the average of 27 adults. My n is 27. This is less than 30. However, my original distribution is normal, so I can also use a central limit theorem. And I'm looking for mu of x bar because I'm looking for the probability of the average. Mu of x bar equals to mu, which is 189. And I'm looking for sigma of x bar, which is equal to sigma over root n, which is 39 over the square root of 27. And I got 7.505553,499. This is not my final answer, so I'm going to leave it the same. I'm going to use all of these digits for my calculation. Everything on this line now is no longer x. It's going to be x bar because that is what we are trying to look for. My mean is 189, and I'm looking for the probability that is greater than 148. Probability of x bar greater than 148. For question B, my mean is still 189, but my standard deviation is different. 7.505553,499. And I still want to find the probability when x is greater than 148. This is my answer. The probability of x bar greater than 148 is 0.999999998. If you round it to 3 significant figures, this is almost 1. Remember, 1 is the whole entire area. This is not 1, right? And also, if you compare this graph with this graph, they both are greater than 148. So this can't just look like this. I can't move this because they are the weight. So in order to make this yellow area bigger to be almost 1, I need to extend my height to make the graph taller because this doesn't look like 1 to me. So it should look something like this. Example 2. Assume that the population of human body temperatures has a mean of 98.6, as is commonly believed. Also assume that the population standard deviation is 0.62. If a sample of size n equals 106 is randomly selected, find the probability of getting the mean of 98.2 or lower. I have mean of 98.6, standard deviation of 0.62. They didn't tell me what distribution this is. However, because my n is 106, which is greater than 30, I can still use the central limit theorem. To use the central limit theorem, I need to find my mu of x bar, which is the same as mu, which is 98.6. And also I need sigma of x bar, which is sigma over root n, which is 0.62 over square root of 106, which gives me 0.0602197235. So my mean is 98.6. Everything on the horizontal scale is x bar. And I want to find the probability that x bar is 98.2 or lower. 98.2 is somewhere in here. And I want it to be lower, which is on the left. So I'm looking for probability that x bar is less than 98.2. I'm using the mean of 98.6 and the standard deviation of 0.0602197235. For example 2, my mean is 98.6. My standard deviation is 0.0602197,235. I want my x to be less than 98.2. This is my answer. This is what I got from StatCrunch. 1.5437e negative 11. This means scientific notation. This means you're going to get 1.5437 times 10 to the negative 11. What does that mean? It means that if you want to convert this into a decimal notation, you are moving the decimal point to the left 11 places. And if the question is asking you to round to 3 decimal places, 4 decimal places, then that is equivalent to 0.